Today, I want to talk about analytical calculation formulas for capacities of classical and classical quantum channels. Existence argument for channel capacity has a following problem. Famous Arimoto-Blackford algorithm calculates the capacity of a classical channel. However, it gives only its approximate value by using iterative algorithm. The precision depends on the number of iterations. Each quantum extension calculates the capacity of a classical quantum channel. However, it has the same problem. Our formula is analytical formulas. So our method calculates the capacity of classical channel and CQ channel analytically without any error. Due to the time constraint, we will explain only the case with classical channel. The same method works for CQ channel. Firstly, we summarize existence result for channel capacity. Firstly, we prepare a relative entropy between the two distributions P and Q in this way. And in our setting, input system is X and output system X. For depending on input element X, we have an output distribution WX. This one is given as a channel model. So we define output distribution when input distribution is QX in this way. And the channel capacity is given as a maximum of the average relative entropy in this way. This is the input distribution, and this one is output average distribution. But this quantity can be written as this minimax model, and minimax, and in this one we can rewrite it in this way. We need to do several preparations. So firstly, we prepare Shannon entropy in this way, and also we use exponential family. This is the key concept on the information geometry. For this M, firstly, we prepare this generator function fjy, and we prepare potential function in this way. So then we obtain this distribution family with this parameter theta. So here our cardinality is an, but the number of function is n minus 1. So this is our algorithm. Assume that input system and output system has the same size in this way. And we define function, generator function f1 to fn such that fij is the inverse matrix of wij. Then we set parameter theta in this way by using Shannon entropy. So here I should be 1 to n minus 1. Then we calculate potential function in this way, and then finally we define function qx hat. So by using the inverse matrix of transition matrix in this way. So in this case, sometimes this one is not positive value. But if all of this quantity, for all x, this quantity is positive, in that case, this C hat is the channel capacity. Otherwise, the capacity is achieved by a distribution with support this one. So if this condition does not hold, this set is a strict subset of X. In this case, we cannot calculate the channel capacity in our method. So here is an analysis on our algorithm. So calculation amount is this quantity, N3. But existence method, for example, that Arimoto-Blackford algorithm, the calculation amount is this quantity, N square and log N over epsilon. So here, epsilon is error, amount of error. If epsilon is go to 0. In that case, this quantity goes to infinity. Our algorithm has several requirements. So firstly, input size and output size should be same. Secondly, this distribution is somehow vector. This one can be considered vector. This vector should be linearly independent because we need to calculate its inverse matrix. And also that q hat function, q hat x function should be positive for any input x. We need 3 conditions. Now we consider a simple example. Assume that x and y should be only 2 elements. So in this case, the output distribution W1 and W2 can be returned in this way, and its inverse is returned in this way, and the potential function can be calculated in this way. Then the capacity is calculated in this way. This is very simple. Next, we consider the case input is 4 elements and output is 3 elements. And also we consider this typical example, W1 is this form, and W2 is this form, and W3, W4 is this one. And we denote the capacity of channel without Wj by Cj. For example, in the case of J equal 1, we have 3 input W. So then the channel composed on W2, W3, W4. This channel is written by C1. So in this way, we define Cj. We use this notation to calculate our channel capacity in this model. So firstly, we consider the case J equal 4. In this case, that C hat is calculated in this way, and here H4 equation is given this one, and that hat function is given this way. So if epsilon is greater than this threshold, all conditions hold, then C4 equal to C4 hat. So we can calculate this channel capacity. Otherwise, the condition 3 does not hold. Then the support of the optimal input distribution is only 1 and 2. In this case, we can calculate the channel capacity C star in this way, and this one equal to C4. Secondly, we consider the case J equals 3. In that case, that C hat is calculated in this way, and H3 epsilon is given this one, and that hat function, Q hat function is calculated in this way, and when epsilon is greater than this threshold, all conditions hold, and C3 equal to the above C3 hat. Otherwise, the condition 3 does not hold, and the support of the optimal input distribution is 1 and 2. So in that case, the capacity C3 equals C star in this way. And finally, we consider the case J equal 1. This is the same as the case with J equal 2. So in that case, the hat is quantity C hat is calculated in this way, and hat function Q hat function is given this one. And in this case, when epsilon is greater than this threshold, all condition holds, and C1 equal to C1 hat. Otherwise, the condition 3 does not hold, and the support of optimal input distribution is 3 and 4. In this case, that capacity is in the case of that capacity is CW star, and this one is calculated in this way. So in this case, in the totally, in summary, our channel capacity is calculated in this way. So depending on the amount of epsilon, we have 3 cases. So first case, the capacity C star, and the second case C4, and the fourth case C star star. So this is numerical plot. So we have several quantities C star and C star star and C4 in this way. So in the small case, red one is capacity, and then we have a green one, and finally our capacity is purple one from here. So we can show the enlarged graph in this way. So C star, so C star. When impulsion is smaller than this threshold, the capacity is C star is greater, green one. And the impulsion is between these two quantity, the capacity equal to C4, and this one give red one. And if the impulsion is greater than this threshold, the capacity equal to C star star. That's purple. This is the conclusion. We have proposed an exact algorithm to calculate the channel capacity of classical channel. This result is extended to the case with the CQ channel. However, we have various conditions to apply our formulas. It is a future problem to remove these conditions. This is references. Thank you very much.